Hi, I'm Mr. Miller, and this is a lesson on connecting graphs and rational equations. So here's the first example. We're going to determine the roots of the equation 14 over x minus x plus 5 equals 0, algebraically and graphically, and we're going to make a connection between these two things. So for starters, let's identify there's a restriction. X cannot be equal to 0, otherwise the first term of the left-hand side of the equation will be undefined. Next, if we multiply all terms by x, then this will get rid of any denominators. And so here's what we get as a result. As you can see, it's a quadratic equation. And if you multiply both sides by -1 and rearrange the terms, it looks like this. So now we're looking for factors of -14 that add to -5. So those factors are -7 and +2. And so that means x equals -2 or +7. And now here's what it looks like graphically. If we graph the left-hand side of the equation, the 14 over x minus x plus 5, that function looks like this. So if we make a table of values, connect all those points to the nice smooth curve, you'll notice that this function, the y equals 14 over x minus x plus 5, has a vertical asymptote at x equals 0, and it has an oblique asymptote, which is y equals -x plus 5. And the roots of the equation are the zeros of this function. So notice that we've got zeros here at -2, 0, and 7, 0. And those correspond to the roots of the equation. Let's take a look at another example. So this time we've got an equation with a left-hand side that's non-zero and a right-hand side that's non-zero. And we want to solve this equation graphically and also solve it algebraically and do a comparison. Here's what we can do. We can start by graphing the left-hand side of the equation, the 2 minus 3x over 2. So in case you're wondering, how can I graph this? Well, it's just a linear function. The y-intercept is 2, and the slope is -3 over 2. So you go down 3, right 2. That allows you to graph this straight line. So that's the left-hand side of the equation. Now, if we graph the right-hand side of the equation, just notice that the numerator does not factor, and the denominator has a restriction that x cannot be equal to -10 over 4, which would be -2.5. So we're expecting that it's going to have a vertical asymptote at -2.5. Now, if we do the long division, here's what we'll get. So changing the right-hand side of the equation into this form, you can see that it's going to have an oblique asymptote with a y-intercept of 1 5/8 and a slope of -1/4. And then it's got this fractional part here. So you can get a table of values, plot a bunch of points. You will notice as you connect the points together with a nice smooth curve that this function, the right-hand side of the equation, has a vertical asymptote at x equals -2.5, and it has an oblique asymptote at y equals -1/4 x plus 1 5/8. Now, the way that you solve this graphically is the roots of the equation are going to be the x-coordinates of the points of intersection of the two graphs. So here's one of the points of intersection and here's the other. And the x-coordinate is -3.3 for this point of intersection, and the x-coordinate here is 1.1 for this other point of intersection. So those are the two roots of the equation. And now just to confirm that by solving algebraically, here's what we would do. We can multiply both sides of the equation by 4x plus 10, which is the denominator. And what you'll notice is that The left-hand side comes out quadratic. The right-hand side is also quadratic. If we move all of the terms onto one side and set it equal to 0, this quadratic equation is a little bit of a nastier quadratic equation because it doesn't factor so easily. So instead we can use a quadratic formula, the minus b plus or minus the root of b squared minus 4ac all over 2a, where a is 5, b is 11, and c is negative 19. So if you simplify this, it's negative 11 plus or minus the square root of 501 all over 10. And evaluating that to one decimal place, you'll get negative 3.3, and the other root is 1.1. So that's a confirmation of what we got graphically. And here is one more example. We've got an equation, x plus 3 over 2x minus 6 equal to 2x minus 2 over 3 minus x. We're going to solve this graphically and algebraically. Compare these, and we should have agreement between the two if everything works out well. So if I do the long division for the left-hand side, we've got 1/2 plus 3 over x minus 3 when I've got it all simplified. So we do have a vertical asymptote at x equals 3. And it looks like we've got a horizontal asymptote at y equals 1/2. So if we plot a bunch of points and we connect them together with a nice smooth curve, we should notice that for this function, the left-hand side, the horizontal asymptote is y equals 1/2. And again, when you change the form into this form, you can see that y equals 1/2 right there. And we've got a vertical asymptote at x equals 3, because of course, in the first place, we know that 2 times 3 is 6, and 6 minus 6 is 0. And anytime you get a 0 in the denominator, it makes that expression undefined. So that's why we have an asymptote there. So now if we graph the other side, so we can make a table of values and get a bunch of points, connect them together with a nice smooth curve. We'll also notice that this has a vertical asymptote at x equals 3 because it makes the denominator equal to 0 here. But then there is an oblique asymptote at y equals 2x. And so here are the two sides of the equation. So now it's a matter of taking that y equals 2x minus 2 over 3 minus x and seeing where it's equal to the left-hand side. And so graphically, the roots of the equation are the x-coordinates of the points of intersection. And so here's one point at x equals 0.08. We're going to take that x-coordinate as one root of the equation. And now it's off the grid, unfortunately. My apologies. I should have made my y-axis go up a little bit higher, but you'd find that at x equals 3.17, the left-hand side function and the right-hand side function cross each other. So those are the two roots of the equation. Algebraically, what we would do is this. We'd take the equation and we would multiply both sides by 2x minus 6. And here's what happens. It divides out on the left. And on the right, what you'll notice is that the 2x minus 6 times 2x, that gives you the 4x squared minus 12x. And multiplying it across this other part, what you'll notice is that, so first of all, what I did was I changed the sign from negative to positive and switched up the 3 minus x to an x minus 3 to match with this factored form with the factor of x minus 3, so that will divide out and simplify things. And if you move everything onto one side and set it equal to 0, we have, again, a quadratic equation. And once again, it's a little bit of a nasty one. This one doesn't factor, so we use the quadratic formula again. So it's minus b plus or minus the root of b squared minus 4ac all over 2a, where a is 4, b is negative 13, and c is 1. And so if you substitute that into the quadratic formula, it will simplify to this. And now if we evaluate to a few decimal places, we get x equals 0.08 or 3.17. And that agrees with what we found graphically, so we know we're good to go. Now, for my pre-calculus 12 students, you may want to have a look at some other examples in the textbook. For instance, example 4 on page 463 and 464 of the textbook. And now that completes this lesson on connecting graphs and rational equations. Thanks for watching, everyone, and have a good day. Bye.